Okay, good morning. Hope everybody's doing well. Um, so we're going to start talking about energy today. Here I can. Hi. So we're going to start talking about energy today, uh, and it's kind of big picture. What I want you to have in mind is that we're transitioning from. We've been talking a lot about forces, Newton's laws, and one of the that can be challenging. It can be complicated because we have to keep track of directions of everything before we're able to um, find quantities like uh, the velocity or something like that. Like we have to of the vector picture, the Newton's laws picture requires us to be really careful and keep track of the directions of all the forces and make sure we don't have them switched around or anything like that. And we're sort of transitioning. So we've talked about work, which allowed us to connect with a scalar quantity, energy, and now we're building on that, and we're going to talk about conservation of energy in this chapter. And kind of one of the big themes, one of the big ideas with this, I think, is that a lot of times it's easier to formulate a problem in terms of energy, to talk about to account for, in other words, all the energy that's in the system, and then solve the problem and figure out, well, how has that energy changed from one kind into another? How can you use that to figure out quantities of interest? Um, as opposed to the force picture where we were working with vector quantities. So that's kind of big picture where we're headed in this chapter. Before we dig in, a couple administrative issues. So one, um, I had some problems with my pen this morning, so we'll see. Hopefully, the whiteboard cooperates. But um, one thing I wanted to mention is so there's a quiz out. It's due tomorrow night. Um, so be sure to get that completed. It's the same format as we had done with the previous one, where there's one part um, that's questions in the homework system, and one part that's a free response question. Folks seem to like this format fairly well, so we'll stick with that. Um, and so just be sure, to get this in by tomorrow. And so I wanted to give you enough time. You had a few days. You'll have had a few days to look at it. I would recommend, do this part first. That way you're not constrained by time. You kind of can review a question. There's also a lot of detail in the email that I sent out about this. Um, see your email for details. There's some uh, uh, pointers about the content, what's in the quiz and stuff. Um, so that's one thing. Another thing that we'll be following up with you shortly is just the final format. So being online, I feel like the end of the quarter is really creeping up on me, and I suspect it might be creeping up on you too. And so I wanted to make sure that we had sufficient time to talk about the final, doing it in such a way that everybody knows what to expect. It's not, it's not holding any surprises for anybody. But I've been brainstorming about this, and I will plan on putting out a survey to ask for some input from y'all. But I want to make sure that everybody's clear with that. So stand by for more details with this soon, and we'll have enough time that we can talk about it a little bit and address any concerns or any confusion beforehand. Um, so yeah, give me a little bit, and I will have more information for you on that. I just want you to feel like yeah, like the process is clear, that you're not getting any like surprises or anything. But it's going to have to be a little bit different than what we've been doing for quizzes, just because we have to look at more material because it needs to kind of span the whole quarter. So those are sort of our reminders. Does anybody have any questions that I might be able to speak to? Um, any questions or concerns? Um, and of course, if you have some question that you'd rather not ask in the chat or something, shoot me an email, contact me on Teams. Any questions? Good. Are you guys ready to proceed? Let's see, questions. Yeah, so that's one of the things that we're trying to figure out, because technically we're supposed to have class during that week, because you know how we had the week off? So I think what I'm leaning towards doing is, and this isn't set in stone yet, but would be to have time available during lab. So half the class has lab on Friday, so I feel like it doesn't really make sense for us to have lab after what would have been the final. So we'll probably use the final time, which would be it would be a bigger block of time, so you'd have 2 hours. But then combine it with kind of what we've been doing, where you have access to some parts. So yeah, I'm still nailing that down, but that's an excellent question, Liam. Because I mean, also there are, yeah, I don't know that the other problem with that is that I think it's likely that your classes will still be meeting during that time, so that the time that's in the original final schedule may conflict with what would be your normal class time in this or other classes. So we're going to have to come up with a compromise there. Um, so yeah, I'm going to look at in detail the schedule so that you know what to expect well in advance. But that's an excellent question. Other questions about these administrative issues? Oh man, I don't even know. I mean, technically, in terms of what week we are in, so technically we are in week 8, but we missed a week. So it's like we're in week 7 of class material, if that makes sense. But this is actually an issue that faculty have been talking amongst ourselves about this, and like everybody, I don't know if you guys are confused by this, but I am confused by it in terms of what week exactly we are in. So if you find yourself scratching your head a little bit, oh yeah, okay, so it is week 8. Um, they didn't change the drop deadline. The drop deadline is still today. Well, I have to nail that down. Tell you what, if the drop deadline is actually today, I have to I'll confirm that and email everybody about that, because that's a hard deadline. So I'll clarify on this because that's important. Oh my gosh, yeah, no, it's just I wish I had thought of the drop deadline earlier to tell you what. I mean, you guys, yeah. No, I feel bad. I sort of dropped the ball on that. I should have thought of more about that drop deadline issue. I will confirm that and get back to everybody. Um, that seems like that would maybe I got an email in my email about that too, but that's an important issue. So stand by. I will get that uh, confirmed and get back to you. I mean, I think folks basically, if you're doing your work, you're doing fine. Um, I will reach out to any students who I'm concerned about. So, um, but yeah, that's so schedule. There's definitely some scheduling issues. I appreciate you bringing that to my attention. I did that totally. I totally missed that or wasn't thinking about that. Um, today at 6 p.m. Okay, okay. Um, so yeah, stand by with that. I'll get back to you on that. Other questions? I guess that's kind of the one that's in the foreground at the moment. Any other questions, concerns, stuff? I really appreciate you bringing stuff like this to my attention so I can then, broadcast it to the larger group because it's obviously if I missed something like that, there's a fraction of the class that's also missing something like that. So, I really appreciate you bringing that to my attention and I will follow up with everybody. Okay, so that's enough admin issues. If you have additional questions or concerns, shoot me an email, uh, contact me in Teams, and we'll get that straightened out. Back to actual physics. So uh, we're talking about just to give you some context. So in chapter 7, we'd been we've been looking at work, and we had looked at the basically the most complete definition of that was the integral if you have a varying force of that force dot dl. So it depends on both. And we looked at a couple of math topics. It depends on both the direction. So we had explored the dot product as kind of the mathematical tool that we use to figure out the portion and the displacement, the portion of the force and the displacement that are aligned, that are in the same direction, and then we could use that to compute work. And we also talked a little bit about integration with regards to the fact that if you have a force that's varying, you have to integrate the force. And that was kind of the first 3 sections. And then in the last section, we talked about how the change in kinetic energy, where kinetic energy is 1/2 mv squared, is equal to the net work. And also it goes, underneath all of this was the introduction of the unit for work and energy, which was the joule. Let's see. All right. The joule, which was, recall, it's a force times a distance, so it had units of kilograms, meters per second squared times meters, and use the capital letter J. And this gets at what I was mentioning at the top about how we're connecting scalar quantity work with a vector quantity forces and displacements. And so where we're going with this is we want to be able to tackle more and different kinds of problems using this idea of energy. And so the first kind of, we're going to add to our toolbox some other kinds of energy. And The main one that we're going to talk about today is potential energy. And before we talk about potential energy, we have to make a distinction about kinds of forces. So this is kind of where we're coming from, and where we're going is energy conservation. So chapter 8, energy conservation. And we'll look at this in lab this week as well. I'm prepping our document. We'll get that out later today for you. So energy conservation. The first thing that we have to do, like I said, is clarify make a distinction between two different kinds of forces. And the reason that we need to do this is because potential energy is only defined for one kind of force. Okay, so the definition that we need to break down here is the difference between something called a conservative force versus something called, well, non-conservative forces. And that definition, actually, I should have it in text here. So give myself a little more space. So this is the definition, one of the definitions that's in your textbook. So a force is conservative if the work done by the force on an object moving from one point to another depends only on the initial and final positions of the object and is independent of the particular path. So I think that the word, the words in here, independent of path, are key. It's kind of a long definition, but independent of path is key. So if a force is independent of the path that you take, the work done by it rather, that's an example of a conservative force. And basically the number one example of this, or how about I call it, a key example of this is gravity. So let me give you a little cartoon to show you what I mean. Suppose you're trying to calculate the work done by gravity lifting an object. So let me give myself a little more room here. So consider the situation, you're lifting an object, right? You can just lift it up. And if you compute the work that you do to do that, well, what is it? You have the force of gravity pointing down, this displacement vector. We can think of this as a vector d that would just be some height. And so for the simple one-dimensional case, the work that you would be doing on that object would be mgh. Now, you could just as well lift this object, go sideways a little bit, go back, goes up to this. You could have a path where you have it on the diagonal. In any of these cases, when you go and compute the work, so granted these are more complicated because you would have to evaluate the dot product. If the force, you would have to evaluate the dot product because the path is not in the same direction as the force the whole time, but the force would still be, just pointing down. And in all of these cases, you would find that the work that you do to lift this up is still just mgh, okay? So in other words, independent of path, okay? So in order for us to be able to define potential energy, we have to be able to be talking about conservative forces. And conservative forces are things like gravity, where it's not going to matter the path that you take when you calculate the work. And so to give you a counterexample, so counterexample meaning a non-conservative force. So it's kind of, I want to show you in person, and then I'll put it up. I'll try and sketch it just so you have in your mind the distinction that I'm trying to get at. And that is, consider, okay, so the counterexample that I want you to think about is friction. So here I have a coffee cup. Try and show you. So I have a coffee cup. This is all right. So I can have this have a starting point and an ending point that's the same, but take different paths. So if I just push it across, there's going to be some amount of friction, work that's done by friction that's associated with that. Now, if I take a different path, there is friction the whole way, right? I am doing work the whole time. In other words, there's more work that's being done by friction if I take a different path. So, if I go like a really circuitous path, it's going to be a lot more work than if I go just directly. And so this is an example of a situation where the amount of work depends on the path that you take. So it is not path independent. It depends on the path. So this would be friction is your, go-to example of a non-conservative force. So friction. So think, top view of like a box or an object on the floor or something. If you go from one position, from A to B, the amount of work that's done by friction like this versus like this is not going to be the same. Okay, so this is an example of it depends on the path. It's non-conservative. Not conservative. Okay. So, and why I'm harping on this, why I'm making such a big deal about this distinction is that we can only define potential energy for conservative forces. So why we care about this, we can only why we care about this distinction, we can only define potential energy for conservative forces. So, what is potential energy? Well, we've talked about this a little bit, or alluded to it a little bit, with regards to gravity, and you actually have the tools that you need to calculate it. So first off, so this is the next section. This is section 8.2. Just qualitatively, potential energy, you can think of this as stored energy. You know, and it can be stored in an object's position. So intuitively, you probably have a sense like if you have a cliff or something and you have a rock that's on top of the cliff, right? This rock has potential energy due to gravity. Okay. But it can also be stored in like the configuration. So, for example, it can be stored in, you know, how things are arranged. So, examples that I think are useful are like, uh, you know, a bow. If you stretch that bow, there is potential energy that's stored, and you know that if you release it, you could uh, uh, fire an arrow. You could use that stored potential energy to do something, to do work. So it's stored energy, or another way to think about it is it's, you know, stored capacity to do work. Okay. So if we think back to our gravity example, if we think of potential energy as stored energy, as the capacity to do work, you have to put energy in. You have to give it that potential energy. You have to put that capacity in there. And so, in other words, you have to do work on the system. So, for example, with gravity, if we were to, you know, we're talking about our simple lift example again. If you lift your object up some height, in this case, we were, you know, you're applying a force that's the same size as the force due to gravity, and you would find, you know, if we use our more correct or complete definition, we would integrate that force over the distance, and you'd find that you put in mgh. Well, the other way that you can think about this is that, and this would be, so you're, here, let me actually give this a little more room. So you have to put energy in. The other way that you can think about this is that it's the negative work done by the force in the system. So this is actually the definition that they use in your textbook. So they use the letter U. I think I like PE because it's obvious that you're talking about potential energy, but if you see U, they're talking about the same thing. So the change in potential energy is negative the force in the system, i.e. it's the negative work. Okay. So if we look at our gravity example with this situation, what would that look like? Well, the force is pointing down, right? The displacement vector is positive, so this quantity would be negative, but we're taking the negative of that work, and so the whole thing would be positive. Hopefully, seeing that in more detail doesn't add confusion, but helps you see, like, so in other words, the potential energy, the change in potential energy is going to be the negative work that you do. So not that you do, that gravity is doing. So when you take the negative of that negative work that gravity is doing when you're lifting the object up, you get a positive mgh. Okay? So this is the main definition, that the change in potential energy is the negative work. And this isn't the net work. This is just the work that's been done by gravity or that's been done by whatever conservative force. Okay? So this potential energy, this ingredient, we're adding to what we already have about how the change in kinetic energy is equal to the net work. So the net work didn't have anything to do with conservative forces. We didn't have that stipulation. The potential energy, though, is the work done by conservative force, done by a conservative force. Let me show you another simple example to hopefully drive this home, clarify this a little bit. So our other, I should let's see here, wait a second. I skipped something that I wanted to mention. Sorry, I kind of went out of order. Let me show you one other piece of information. Another way that you can think about conservative forces. So actually, let me see here. Can I? So sorry, this will be a little bit out of order, but another way that you can think of so I was just about to talk about another kind of conservative force, and it occurred to me I didn't make this other point. So another way to think about conservative forces is that if you make a loop with that force, the net work that's done is going to be 0. So in other words, in our two examples, gravity, if you lift an object up and then bring it back down, the work done in this situation is going to be 0. Instead of, for example, if you look down on top of, so thinking about like a path, my example with the coffee cup on the table, on the clipboard, if you move that coffee cup around, the work is not going to be 0. So I meant to mention this up above, but this is another way that you can think about this. Basically, if you do work on any closed path, it's going to be 0 in a conservative force. So gravity, you lift an object up and then you come back, it's going to be 0. Friction, you move the object around, you come back to where you started, the work is not going to be 0. And you can kind of see that here, like with the gravity example, while you're lifting the object up, in that situation, for this part, this would be doing negative work, and then this would be doing positive work, and when you add it all up, you get 0. Okay, so sorry that's sort of out of order, but this is another useful way to think about conservative forces. Okay, so back to our definition of change in potential energy equaling negative work. The other example that I wanted to show you is the other system that we've looked at a little bit in terms of integration was the spring. So another example, excellent example, is the spring to talk about this. So recall, you can kind of think about this in terms of what I've just talked about, a closed path, right? So like if you take a spring and you stretch it out, when you do that, it's going to be doing negative work, right? You've stretched it this distance, but the force is pointing this way. Then when you let it back, or here, let me, if you then let it go back to its equilibrium position, the displacement would be the opposite direction, right? But the force is still pointing back. And in that case, the work would be positive. And when you add them up, the net work would be 0. So hopefully this helps you see that a spring is a conservative force, or the spring force rather, is conservative. Okay, so we can evaluate the potential energy that we put in a spring by using this same idea. So what we would do is we need to find the negative work. To find the work, recall for the spring, we would integrate the spring force, negative kx. Let's integrate it. Let's say that we moved our spring, from 0 to x final. How about? So from 0 to x final. When we do that integration, the integral of something times x, you're going to get x squared over 2. Notice we have negative times negative. It's going to be positive. Oh, and I left out the k here. So this becomes positive kx squared over 2, evaluated from 0 to x final. You're not going to get anything from the 0, but you would get that the change in potential energy is going to be 1/2 kx final squared. So this is for a spring. So notice, what did we do? Just to reiterate, we integrated the spring force to find the work. The change in potential energy is the negative work. So we end up with the positive quantity kx squared over 2. And that's the potential energy that's stored in a spring when you stretch it. Okay, so, and this may seem, not super exciting, but there's an ingredient that we can add to this. Or how about, are there any questions so far? Let's take a second. I've been talking a lot. Questions? Is everybody doing okay? Good? Clear? You're all comfortable with this? Yeah, basically just swap the sign on the work is how you can think about it. I think for folks who have seen integration a fair amount, it's maybe not so intimidating. Maybe if you're less familiar with integration, it's like, wait, what are we doing? Like it's another version of kind of the same thing. I think of it just that uh, if you want to store energy in something with one of these forces that allows you to do that, that's conservative, i.e. gravity, a spring, something like that, you need to put energy in, and that is the same thing as saying that the system needs to do negative work. So, yeah. All right, so let me show you something that's sort of complementary to that, which I think is kind of cool. So far we've talked about how uh, the potential energy, or your book uses the letter U, um, is basically the negative integral of the force. Well, we can also do the sort of complementary operation, which is, what if we don't know the force, but we know the potential energy? Well, you can get the force. So imagine if you take a derivative of both sides of this, right? The derivative would cancel the integration operation, but you would have to take the derivative of the potential energy. So in other words, the force is given by the derivative of the potential energy. Okay? The negative derivative of the potential energy. So this may seem like, meh, same old, not that cool. But why this is kind of cool is that, remember, I've been harping on the idea that we're able to now work with energy, a scalar, rather than always having to use forces. Well, suppose you wanted to know the force due to some potential, you can get that with this. So this allows you to find the force, a vector quantity, from a scalar. From a scalar quantity, well, let me put it to you this way. From energy, from potential energy, a scalar quantity. Okay, so this speaks to this what I've tried to convey, which is that a lot of times it's easier to set up a problem, set up a situation to state the facts of the problem in energy terms, in terms of potential energy, but then you can find the force that's going to act on something by taking the derivative of that, which is pretty neat. So let me show you what this looks like in terms of our unit vectors, right? So if you wanted to find, so this is kind of the these two, these complementary operations, complementary pictures for force and potential energy. And let me flesh out to you what this looks like in terms of a vector. Excuse me. Oh. What is going on here? Sorry. So consider if you have a force, or you want a force that's a function of your coordinates. How you get that is the following. It will be equal to the negative I hat times the derivative of your potential with respect to x, j hat times the derivative of your potential with respect to y, k hat derivative of your potential with respect to z. And you'll notice I've drawn these derivatives a little bit different with like a script d instead of a d. That's because these derivatives are partial derivatives. Have you guys encountered this terminology before? Calculus is magic. No, I agree. Calculus is really the way, it's sort of the language of physics. I think a lot of stuff is sort of more concise. It can often be more more clear in calculus. Um, so yeah, so it sounds like a few people. I'd like to hear from more folks about their experience with partial derivatives. Like, don't think so. It's totally fine if you haven't seen it. I wouldn't necessarily expect you to have seen this. We're going to talk about this in one lab exercise as well, so it's not totally in isolation here. So it's fine if you haven't encountered it. Yeah. What about other folks? Let me know in the chat. Can't remember. So you may have seen it. So just a real quick. So a partial derivative is basically just a derivative where you treat everything else as if it's constant. So for example, so just sort of a math aside, you do your normal derivative rules depending on what the function is. You treat everything else as if it's constant. So I think if you haven't seen it before, you might be like, oh my gosh, what is this? Do I have to know like other rules? No, you don't have to know any other rules. You just have to see it in action. So for example, suppose our potential is, it's a function of x, y, and z. Let's just make it something simple. X squared, y, z squared. Okay? Now, if you go to find the force due to this potential, it's going to be negative I hat times the derivative of this thing with respect to x, as if the other things, we just hold them constant. So this would be, you pick up a factor of 2x times your constants. Okay? I think you kind of see the deal here. So for, the j hat contribution, we'd have negative j hat. X squared appears as a constant. Y would go away. Z squared. Our k hat piece, the derivative of our potential with respect to z, we would pick up a factor of 2. Everything else appears as if it's constant. We'd have that. Okay? So it's not something to be afraid of. We will actually revisit this in the context of error. So I'll put a note here. My pen. Oh no, pen problems. Uh-oh. So my pen stopped working here. Oh man, writing with my fingers. Oh, way worse. So we'll revisit partial derivatives in the context of error propagation. So because it so happens that what you can do is you can look at how a quantity depends on another quantity. No, we won't use it tomorrow. You won't. You don't need it for tomorrow, but we'll come. We'll talk about it in a future lab. And basically, the idea is that this math is also useful for you if you have a function that depends on things. To see how it depends on those things, you take partial derivatives. So don't worry if you're like, oh, this is another math topic. I'm a little bit, I haven't seen this before. We're going to touch on it in lab as well. So, and I think that's all I want to talk about because I'm having problems with my computer or with the pen entry or whatever, and it makes it hard. We had tons of problems with this morning, so I'm going to see if I can get some batteries for the pen and if that fixes the problem. But otherwise, do you guys have any questions? We'll be looking at some examples tomorrow, or not tomorrow, on Wednesday. So I will either see you tomorrow in lab. We're going to be doing a lab on energy conservation, or I will see you on Wednesday in class. Propagation. Propagation. Oh my gosh. Sorry, it's way worse to try and draw on here with my finger. Yeah, it won't let me. Other questions? Yeah, why is my pen not? Oh, there, it's working. Okay. It's working. Yay. So, yeah, no, we'll come back to partial derivatives in the context of error propagation. Let's see. Is that F? Oh, sorry. No, this would be the force. The force would equal. Yeah, good catch. I left out the equal sign. Yeah, thanks for pointing that out to me. Other questions? Clarifications? I will follow up with regards to the administrative issues we talked about. So stand by for that. I'll get back to you in a little bit. Okay. Of course, if you have other questions, shoot me an email, reach out on Teams. We can communicate. So otherwise, have an excellent day. We'll look at some examples next time.